Okay. Okay, everyone. Let's continue where we left off with your favorite topic as of yet. Okay. So, Jason, join the crowd. Okay. So what are the different species of matter that can be analyzed using spectroscopy? Yes, Kia? Molecular and atomic species. And within those species, there are obviously different molecules and different atoms. Okay. Name the different forms of radiation-matter interaction. Don't look back at your notes. Whatever you remember. You don't remember, you don't remember. I just want to see what information you retain. Nothing. What kind of interaction? Yeah? Thea? Absorption. Thank you. What's that? Emission. Are you excited about that? Okay, other interactions like diffraction of light, reflection of light, light scattering. So these are all different forms of interactions with light. Okay. What are the spectral regions most relevant to food analysis? Laura? UV and visible, and there's another one that is very important. We haven't learned about it yet. IR. Okay. What are some applications? No, before that. Name spectroscopy / spectrometry analytical techniques. Okay. Absorption spectroscopy. NMR is one. Yes, NMR is one. Absorption spectroscopy, emission spectroscopy, atomic absorption spectroscopy, IR, mid-IR, near-IR, FTIR, all of them, mass spectrometry. Okay. Spectrophotometer is the instrument that you use to determine absorption or fluorescence. Huh? Spectrophotometer is an instrument that you use to do spectroscopy. It's the name of the instrument. Atomic absorption instrument is a spectrophotometer, but it's atomic absorption spectroscopy. Mid-IR instrument is mid-IR spectrophotometry. Yeah. So, okay, what are some applications for spectroscopy spectrometry? Anna? Quantification of different components. Yep. What else? Identification. Sophie, what else? Compositional analysis. Okay. So identification, quantification, composition, detection of presence, forensics. So all of that. Okay, this is for later. Let's continue talking about characteristics of light. So we have the wave-like characteristics, and we do have the photon-like characteristics. So let's start with the wave. It's relevant in certain types of spectroscopy, but in food analysis, mostly we talk about photon of light, but I will just remind you about the wave-like properties of light. So you have an electric field and you have a magnetic field. Okay, so you have, that's why it's called electromagnetic radiation. So you have the electric field represented on the E-axis, and then you have the magnetic field represented on the B-axis. So, and then certain terms that you want to know, this lambda is a wavelength. So you'll hear lambda. What is lambda? Is the wavelength. And the wavelength is the length between two optima. So you have an oscillation. So you have this oscillation within a wave going from the 0 point here up to a maximum amplitude. So that is the magnitude of the electric vector. So you go to a maxima and then goes down to a minima and then go back up. So this, from this up to this up here, this is your wavelength. So the narrower the wavelength or the shorter the wavelength, you'll have more oscillations within a certain unit in space. When you have more oscillations within a certain unit, you have more energy. You have higher energy, higher frequency. So the number of occurrences, the oscillations that repeat within a unit of space. The more you have oscillations, the more you have energy. Okay? And then the shorter, that means the shorter the distance between these two optima, the more of them you have in unit space, the more energy your wave will carry. Okay. Other properties, let's talk about them. So we have the interference, diffraction, and refraction. So interference is very important. I'll just introduce it here, and then when we get to IR, I'll explain how it's applied in the IR spectrophotometry. Okay, so here what it means, interference, when you have two different waves in space, and they interfere with each other. They cross paths. So when they cross paths in a manner that they are in phase, that means they align, the optimum align with each other. So the optimum here aligns with the optimum here, and so on. Then when they interfere, when they cross path in space, they amplify. So you get the amplification of, you get higher energy out of that. So you amplify the wave. But if they interfere where the maximum in one wavelength interfere with the minimum electric wave, you get cancellation. So they cancel each other and then nothing, you don't get any energy. So in IR, they have the instrument set up in a way where wavelengths interfere with each other, and therefore they can enhance sensitivity of the equipment. And then we can talk about it when we get to IR. I just want you to remember now what interference is. Diffraction is very important as well, characteristic, because we use it quite often when we do quantification. You want to quantify at a singular wavelength. So you want to determine the concentration when the molecule absorbs at a singular wavelength. So oftentimes instruments have a grating or a prism that will diffract the light. So what happens, what that means is that your incident beam, the whole light, whether it's UV light or visible light, hits that grating system, and then the light gets diffracted into singular wavelengths. So you will have the different light at different wavelengths separated so that you can isolate and select particular wavelengths to measure absorption at. And then you have the refraction, which is the principle of refractive index. When you measure total solids or total soluble solids, it's based on the correlation or relationship between the angle of refraction and the concentration in the sample. So when the light hits, when the light is traveling in one medium and then enters another medium, let's say refracts, you have an angle of refraction. It changes direction a little bit. So it doesn't continue going in the same direction. It just changes based on the constituents in the medium that it's entering. So the angle of refraction is then correlated with the concentration in your sample. And that's, in simple terms, refractive index. That is what refractive index is based upon. But like I said, in absorption spectroscopy, when you're doing absorption or even emission spectroscopy, we really look at the light as a photon characteristics or photon properties. So, and the wave carries discrete pockets of energy. And these discrete pockets or packets, whatever you want to call them, are photons. So when we think about interaction of light with your species, whether it is atom or molecule, we think about interaction of a photon or absorption of a photon of light or multiple photons of light. So the energy of the photon is related directly to the frequency. So how many oscillations we have in a unit of space or unit area or unit distance in space. This is a constant, the Planck's constant, but what you want to know here is the energy is directly related to the frequency. So higher frequency, higher energy. Higher frequency means shorter lambda. Shorter wavelength, higher frequency, higher energy. So that's what you want to remember. Okay. Now let's talk about things that we will come across when we learn about the different spectroscopic methods. So monochromator light. What do we mean by monochromator or monochromatic light? Mono, one, singular. Okay. So it's an electromagnetic radiation composed of waves having a single frequency and one wavelength. So having one wavelength, that means they have a singular frequency. That is the monochromatic light. And this is very important for Beer's law. When we talk about Beer's law, if not today, Monday? What are we, Friday already? Okay, Monday. So no, I lie. Monday and Wednesday of next week will be Gary with mass spectrometry. Come back next Friday. Okay, so it's very important for Beer's law. Does anybody, you all heard about Beer's law before? Okay, what is Beer's law? Just, can you remember what it is? Huh? Somebody's whispering. Who knows? Whispering the answer, Alex? Hayden whispering the answer? Come on. Who heard about Beer's law before? Just one person heard of it? Two? What? I'm sure you all heard about it before.
Doesn't the equation have, it's like E raised to some power?
There's no power actually in this equation. But in simple terms, don't think about the equation. We'll get to that equation. You don't have to remember it now. What is it? In simple terms, what's the law? What is the law about? No. Ali's smiling at me from the back.
Like measure light?
Is that about radiation?
Okay. All right. It's the linear relationship between absorption and concentration. Okay. So in simple terms, there is an equation. I'll show you the equation next time, which is absorption equal molar extinction by the length, path length by the concentration. That is the equation. But I wasn't asking about the equation. In simple terms, it's the linear relationship between absorption and concentration. This is what allows us to quantitate. And what allows us to quantitate is having a singular wavelength. So absorption at a singular wavelength. That's part of the law of Beer's law. You cannot do quantification if you have multiple wavelengths. It has to be at a monochromatic light or wavelength. Okay, so keep that in mind, the importance of monochromatic light. Okay, so monochromatic light, in order to have monochromatic light, we have to have monochromators. Okay, so that means in my system, whatever it is, the spectrophotometer that I have, it has to have, or not all of them, but some of them have a monochromator. So what it does is inside of my system, I have my incident beam that comes from a lamp. The lamp could be a UV lamp or a visible lamp, or a very specific lamp for a mineral that you will be using next week and learning about next week. So your light is coming here and it's hitting a mirror because you want to contain everything in a small space. So you use mirror to reflect the light, and then it gets reflected to a grating system. It can be a grating system like this, or it can be a prism. What happens is when the light hits the grating system or the prism, it diffracts into multiple wavelengths. And then you have an opening with a specific slit or a specific dimension to allow one particular wave of a part, not one wave, multiple waves, but at one singular wavelength. So only the waves with a singular or very narrow range of wavelength will pass through. And then you would have a monochromatic light or beam. Then it gets to another mirror that gets reflected to where your sample is for absorption. So that is the monochromator that allows for diffraction of light and selection of waves at a singular or narrow wavelength. Photon flux is another term that you would hear, and it's basically the number of photons flowing across a unit area, perpendicular to the beam per unit time. Just remember what it is, but it will come later when we talk about intensity. Well, I'm going to talk about intensity, brightness and radiant intensity, which is proportional to the energy or joules that hit a unit area per second, so per time, per unit time or per second. Okay? So the intensity is very important because it also helps with the threshold and sensitivity of your instrument. So sometimes you use ways to enhance brightness of the light source or dim the light source. So it really varies depending on what you're looking for. So keep those definitions in mind for later. So here's what I want to remind you: higher frequency, shorter wavelength. So when you see many oscillations in a unit of length, that means you have more frequency. So the energy increases as wavelength decrease, and you have more frequency. Okay, so you go from gamma radiation, X-rays. This is the area most relevant to us in food analysis. Ultraviolet radiation, visible light, infrared radiation. So this region is where most of the analyses happen. So here I'm emphasizing that we're going to focus on the particulate properties of light, photon, and then looking into the absorption of a photon of light or the emission of photon of light. And here we're looking at how that happens in terms of an atom. Either it can be a singular atom or atom in a molecule. So what happens is when a photon of light hits an valence electron, that means an electron in the outer shell, if the energy is within the capacity that is allowable for the atom to absorb, because every atom has allowable energy to absorb, if that photon is within the allowable energy, then what happens is the photon of light is going to be absorbed by that electron, and the electron is going to jump to a higher orbit or shell. So it's going to go up a level. And that brings it to an excited state. So when an atom in a molecule or an atom, singular atom, absorbs light or photon of light, it's going to jump to an excited state. Okay? It won't stay there. It will eventually go back into its ground state. It can do that by two mechanisms. One is just dissipation of the energy as heat, and then goes back to its ground state, or a combination of dissipation of the energy by heat or emission of another photon of light. So that would be the emission. Emitting the energy as photon of light, but because part of the energy has been dissipated as heat, then the photon of light emitted, does it have the same wavelength as the photon of light absorbed? Think about it. Take a minute or a few seconds. A photon of light hit the electron. Electron went up to the higher orbit. And then it dissipated a little bit of heat, and the rest of the energy was emitted as a photon. Does the photon that got emitted has the same wavelength as the photon that got absorbed? No. What would it have? Higher wavelength or lower wavelength? Lower wavelength, thank you. So it would have lower energy. So, no, not lower wavelength. What? Confusing me now. No, it will have lower energy, so it will have longer wavelength. Okay. Friday, we're all ready to go home. Okay, I can. So when the photon hits the electron, and the electron gets excited and goes up to the higher shell or orbit, it eventually wants to go back to the ground state. So it will dissipate some of that energy as heat, and potentially some atoms or molecules can fluoresce. That would mean that will emit a photon of energy. But part of the energy is emitted as heat, so there's less energy left. So the photon that is emitted has lower energy than the photon that was absorbed. So lower energy meaning longer wavelength. So always when you later on in life, potentially you're going to encounter or do an analysis that requires measuring fluorescence. So you will always have to set your spectrophotometer to an absorption wavelength and an emission wavelength. And the emission wavelength is always longer than the absorption wavelength. So when you set up your instrument, you will have to do that. Okay. So when the molecule is struck by photon, it may absorb the energy. Not every time it will absorb. Like when we talked about the spectra from the HPLC last time, there were wavelengths at which you don't see any absorption, right? And there are other wavelengths that you see an absorption. So different molecules, different atoms absorb at different wavelengths. So there are allowable energy that the atom or the molecule can absorb, okay? That's why we see absorption at certain wavelengths, and other wavelengths we don't see absorption. So, but let's say the photon carries the energy that's allowable and it got absorbed, then you get this difference in energy from ground state to excited state. And the difference in energy, again, is equivalent to the frequency of that photon, that light that was absorbed. Okay, this is the point I was saying, but it's stated here in a different words. But basically that the energy that it gets absorbed is not in a continuous manner. So the level of energies that are allowable within an atom or a molecule is not continuous. It doesn't go like 1, 1.1, 1.2, 1.3. It's not a continuous scale. It is a discrete steps of allowable energy that are not continuous. And this is what it is. So you have the ground state, you have an excited state, first level, second level. These are the allowable energy levels within a molecule or an atom. And these are different between different molecules and different atoms. That's why you have different spectra, or that's why you have a unique fingerprint for atoms and molecules that absorb light. So these levels are unique for each compound or each molecule or each atom. So we have three different types of energies. We have electronic energy. So you can see that the electronic energy is the largest energy level, or the highest energy. And you have E0, that's the ground energy level for electronic, E1, E2, and so on. We also have vibrational energy, and these are smaller or carry less energy. And then we have rotational energy, and also this carries less energy. So the pockets are less in energy. Okay, so electronic energy is basically the energy we just explained, which has to do with the electron. The electron absorbs the light and moves to the next orbit. So that is the electronic energy. So atoms or molecules can be excited by electronic energy. So it is the energy that is absorbed by valence electrons, or electrons that are participating in bonding. Again, these are the electrons on the outer shell participating in bonds. And the energy to be absorbed has to be within the energy of the UV visible radiation. So electronic energy is the energy associated with the UV visible radiation energy. So the wavelength within that range allows for electronic energy absorption. So when we talk about absorption or emission of light and gaining electronic energy, that would be in the UV visible range. So the vibrational energy, it has to do with the bonds. So bonds within a molecule. So an atom does not have vibration, or does not vibrate. Atoms within a molecule are bonded together by sharing electrons. That bond vibrates upon absorption of energy, and that we call vibrational energy. So it's only for molecules, and like I said, it's of a lower energy, and it's also quantized. That is, every molecule has its unique vibrational energy that is allowed to be absorbed, and then it kind of overlaps with the electronic energy, but it is less energy than the electronic energy. So you see several levels of vibrational energy within one energy level of electronic energy. And the vibrational energy is in the same range as IR radiation. So in IR, we will learn later about mid-IR, near-IR, FTIR, Raman spectroscopy, all of this. These are the radiation that are responsible for vibrational energy. Will be stretching and bending and vibration of the bonds. Again, we'll talk about that in that lecture. The last one is the rotational energy, and it is basically the rotation of the molecule around the center of gravity. This has no application in food science or food analysis because it is we don't use it for any measurements, any particular measurement, and it's associated with the radiation of the microwave. So we don't usually use that. Again, it's smaller pockets of energy, and it is smaller than vibrational energy as well. So these are the different levels. So there are different rotational levels. So if we want to look at the total energy of an atom or a molecule, atom does not vibrate and there is no molecule, there is no center for gravity. So atom can only have electronic energy, can only absorb electronic energy. Whereas a molecule can absorb electronic energy, vibrational energy, and rotational energy. So, like I said, each of these are unique for a particular atom or molecule, and that is why we can use this very unique absorption of different energies for identification and getting this unique spectra for different molecules, such as this. So every molecule has its own absorption spectra, so the different wavelength at which molecules absorb is dependent on the allowable energy for each of these molecules or atoms. And this allows for separation, or not separation, identification or differentiation between different molecules or atoms that absorb light. I think we talked about emission of radiation. So this is basically the fluorescence, where the photon of light is absorbed, and then it can be emitted, or part of its energy is emitted as another photon of light at a longer wavelength. We talked about this. It's just explaining fluorescence spectroscopy is based on the emission. Again, not all molecules can emit light. Some molecules that can emit light, we can use them to measure fluorescence, and fluorescence is more sensitive than absorption. Okay. This is what you're going to do next week. We still have time. I'm going to start another topic, continue the topic. But I just want to remind you that next week we are still continuing with the rotation labs. So we will have the mass spectrometry lab, LCMS lab, and atomic absorption for determining mineral content, iron and calcium in different food products. So today I'm going to send you an email so that each group know what food product you will be analyzing, and that food product is going to remain with you for several labs. So you will be doing mineral analysis, ash, moisture, protein, fat on the same product. So I will send you an email for that. And for the LCMS lab, we will be determining or identifying different isoflavones, which are phytochemicals, using electrospray ionization mass spectrometry. Gary's going to talk about the theory next week, but we're going to start the labs next week for some of you. Okay, and make sure to read your chapters in the book to help you understand, given that some of you will do the lab before theory. And there will be lab addendum for the atomic absorption. However, you're going to use the chapter 9 in your manual for the MS lab. So you will be needing the manual and the addendum, depending on which lab you're doing. Okay, so this is lab. I'll send you an email with details. Now we're going to dive into the different analytical spectroscopy, analytical methods. Back to the Beer's law. What do we know? we don't know anything, that's fine. We're going to talk about all of this. But B seems right? Yeah, it is right. Anything else? So I think B is the only correct answer. So we'll talk about molar extinction and what it means. And also we'll talk about the fact that the incident beam, that means the light that hits the sample, some of the molecules are going to absorb some of that light, and then the rest of the light is going to be transmitted through the sample. Incident beam minus the transmission beam is not equal to absorption, and we'll talk about that because not all of the light is going to be go through. Some light is going to be reflected, some light is going to be scattered. So not the incident minus the exit beam or transmitted beam is not equal to the absorbed light. In both absorption and fluorescence spectroscopy, no? Go ahead, please. A for sure. A for sure. B is not, and we'll learn about that because there is no linear relationship between the transmission of light and the concentration. There is a linear relationship between absorption and concentration, and we like linear relationship. So it's not linear, we don't use it. A grading monochromator is needed in most cases, yes, especially if you want to do quantification. So you want to have a singular, you want to quantitate at a singular light wavelength so that it follows Beer's law for quantification. So UV vis, in UV vis you can have absorption, you can measure fluorescence. So you can do qualitative analysis or quantitative. Qualitative is for detection of a presence of a component or for identification. So detection of presence or identification of that compound, or what's the molecular composition of that compound. So qualitative and quantitative, where you actually measure the concentration. But however, to be able to do that, to be able to run qualitative or quantitative analysis using UV vis spectroscopy, you need interaction with light, obviously. So you either have an inherent signal, that means your compound naturally is a chromophore, so you can measure absorption at UV or visible or fluoresce naturally, you don't have to do anything about it. Or it does not absorb or emit light. So sugars are not a chromophore. So you have to do something about it. You have to induce chemically a light, or not a light, induce chemically the phenomena of absorption or interaction of light. So it's used to quantitate macrocomponents. We will have a lab on total carbohydrate by phenolic sulfuric acid, phenol sulfuric acid method. Here the carbohydrates do not absorb light, so we have to react them with another compound that gives you a color so that you can measure absorption. So this will be an assay that you'll be doing in the lab. Quantification of microcomponents. So here we do, for example, we learn about that in vitamin analysis lecture, where thiamine is a vitamin that is determined, or the concentration is determined by fluorometric method, where you measure the fluorescence. Another indirect means of measurement, so enzyme-linked immunoassays or ELISAs. These are used to determine the presence of allergens or mycotoxins or many different types of compounds. But for allergens, for example, it's a protein. It needs to be interact with an antibody. But when they interact, you need to determine that interaction, you use an enzyme that you link to the antibody, and that enzyme you add a substrate that will convert that substrate to a product that absorbs light. So if an antibody is bound, that means there is an allergen in your system. You have that enzyme that is bound to the antibody. When you add the substrate is going to react with the enzyme, gives you a compound, and you can measure absorption. If there's no interaction, there will be no compound that would be measured for absorption. Okay. So we're looking to determine concentration. We relate that to the amount of light that is absorbed from a reference beam as it passes through the sample. So now here's your sample. You often have your sample in a cuvette, and you'll be doing that in the lab. So you put your sample in a cuvette, you put it in the path of a beam or a light, and then the light is going to travel for a certain distance. The B is the distance, and then every compound will have a unique absorptivity because it has a unique spectra or absorption at different wavelengths. So it will have a unique absorptivity for that light that is passing through, and it will absorb light. The more concentration you have, the more absorption of light that will happen, and the rest of the light is going to pass through. So this is your incident beam, and this is your exit beam. So as the concentration increases, your exit beam will be lower, the concentration of your chromophore. So the absorption is directly related to the concentration of your analyte. So this is the relationship of transmission. So transmission is the ratio of the exit beam to the incident beam, and percent transmission is this ratio by 100. It's not a linear relationship with concentration, so we do not use it to measure concentration. And here is the incident beam is not equal to or the fraction of the incident beam that is not transmitted does not mean equal absorption, because when the light hits, some of the light can get reflected, some of the light can get scattered by the particulates. So not everything that is not passed through, that means it got absorbed. Absorption is related to transmission. It's the negative log of transmission, and it does have a linear relationship with concentration. That's why it is used to determine concentration. And here you are, this is Beer's law. Beer's law is also Beer's-Lambert law. So if you hear Beer's law and you hear Beer's-Lambert law, it's the same law. I don't know why Lambert was dropped. Both of them were the scientists that came up with that. Maybe for ease of use, it's Beer's law. So it's the relationship between absorption and concentration. So here's your absorption. C is the concentration of absorbing species. It can be in molarity, millimole, milligram per mil, percentage, any type of unit. You can have that concentration based on how you prepared your standards. B is the path length through the solution. So the path of light through the solution, the distance that the light passes. And absorptivity has the unit is the inverse for the unit of length, centimeter, and the concentration, whether it is whatever these units are. Therefore, absorption doesn't have a unit. Everything cancels out. So absorption does not have a unit. So A stands for absorptivity, but when you see this sign here, the epsilon sign, is that what it is? Yeah? Okay, so this means that it's a molar absorptivity or molar extinction. They all mean the same thing. If you read molar absorptivity, that means the unit is in molarity. If you don't hear the term molar absorptivity or just absorptivity, then the unit is not necessarily in molar. And again, this is unique for every compound or atom that you are trying to measure. So absorptivity is a proportionality constant dependent on molecular properties of the species, wavelength, chemical environment. Common sense here. A is common sense. B is common sense. C is common sense. Okay, so molecular properties of the species, definitely, because every species has its own allowable energy for absorption. Wavelength, you would have different absorptivity at different wavelengths, right? So different wavelength, you would have different amount that could be absorbed. So yes, and chemical environment, let's say pH, might impact the ionization status. So you might have differences if the molecule is ionized versus not ionized, you have different absorption. So all of them are correct. Okay, I'm seeing half of you falling asleep, unfortunately, so I will let you go a minute early.